We're looking at inverse functions and how they pertain to logarithms and exponentials. So what is an inverse? Do y'all remember? An inverse undoes what you did to a number. So if I plug a 3 in and get a 5 out, if I take the equation for the inverse, I would plug a 5 in and get a 3 out. Okay? So it undoes what you do when you find the inverse. If you plug the answer in, it takes you back to what you plugged in. Another way to think about it is a reflection over the line y equals x. So it's symmetrical on both sides of this line. Algebraically, we switch x and y switch places. Same thing with graphic, like I showed you here. If 3, 5 is a point on the function, then 5, 3 would be a point on the inverse function, okay? And I want to be clear about one of the words that we're using, inverse versus inverse function. I can find an inverse of just about anything, but our question is mainly going to be, is it an inverse function? So we're just going to do this. You did this last year, but you may have forgotten. Here's our function, f of x equals 2x plus 5. Now we're going to find the inverse. And how do we find the inverse? Step 1, switch x and y. We don't have a y, so we're going to put a y in. Right? And now we're going to switch. So we switched x and y, and now we will solve for y. So we have x minus 5 equals 2y, right? We'll move the 5 over, and now we'll divide by 2. So we have y equals x minus 5 over 2. And now we'll write it in, and that should say f of x equals, okay, 3 replace y with the inverse symbol, right? That symbol did not quite print right. I think it's a printer issue. So now if I plug 1 in, now notice this says f of 1. I'm going to write it here because that's too small. F of 1 equals, so if it's f, we plug it back into f. So 2 times 1 is 2 plus 5 is 7. So now if I plug 7 in, right? If I plug 7 into the inverse, which is this guy right here, 7 minus 5 is 2, and 2 over 2 is 1. So you can see how plugging a 1 in gave us a 7. On the inverse, plugging a 7, well, I said 1, I wrote 2. Plugging a 1 into the function gives you a 7. Therefore, plugging a 7 into the inverse gets you back to a 1. Does that make sense how the numbers switch? This is one way that you can test to see if something's an inverse. Take any point, plug it in, and see if x and y are switched. Let's do the inverse for this one. We can always find an inverse, right? So we'll switch, we'll put a y in, then we'll switch x and y. Then we'll get y by itself. So I have x plus 4 equals negative 1/2 y squared. Multiply both sides by negative 2. So I have y squared equals negative 2x minus 8, right? And now I have to take the square root of both sides. When you take the square root, what do we get out front? Plus or minus, right? So that's the inverse, but it's only an inverse. Let me write it like this. Okay, we can't say f of x, because this guy is not a function. Why isn't this a function? That's a square root function, right? So it should look something like, well, it's going to go backwards, but it should look something like that, and you're going to get a second half to it. And let's test that out. If I put -4 into g, -4 squared is 16, -1/2 times 16 is -8, and -8 minus 4 is -12. Now, if I take -12 and put it into this guy, -12 times -2 is -24, or positive 24. 24 minus 8 is 16. We get plus or minus the square root of 16, which is plus or minus 4. So here we had -12, and on this side we get -12/4 and -12, -4. So this is not function. Okay, and most of the time, this demonstrated to you that you can find the inverse, but many times in math, they're not just asking you for the inverse, they're asking you for the inverse function. So this one doesn't have an inverse function. Let's look at why. You may remember this from our parent functions. You all know the vertical line test. If I draw a vertical line through something and it only touches it once, then you know it's a function. Well, there's also a horizontal line test, which tells us if it's 1-to-1. If you can draw horizontal lines and you only hit the function once, then the inverse is a function. If you draw a line across and you hit it twice, then the inverse is not a function. Okay, so we were able to tell numerically, right? Because we all know for a function, every x only has one y. And for this one right here, we had two different y's, 4 and -4. So like I said, it's kind of going backwards. We knew that because it was upside down, it was negative. But we also know any quadratic is not going to have an inverse function, right? Now, how you'll see this, sometimes you'll see a problem written like, just to show you so you don't wonder. Now, you know by looking at that it's not a function because it's a quadratic, and you know quadratics are don't have inverse functions because they're not 1-to-1. So sometimes you'll see this, or you'll see you'll have it, x will be greater than or equal to 0. And that way you can't plug in the negatives and it will only give you half. So sometimes when you're working out a problem, you'll see the notation where they tell you on one of these x is greater than 0. If it is, then it can have an inverse function. Okay, so the big deal for you to take away from this is that to find the inverse, you switch x and y. And if it passes the 1-to-1 test, then its inverse is also a function. Okay, so basically that's going to get rid of our squares and fourth power. They're not going to be, because both ends go the same way. So we're always going to hit twice. We already did check to see if they were 1-to-1. You know that 2x plus 5 is a line that goes like that. And 1/2 x squared minus 4 is a parabola. Well, it's down at 4. Is a parabola that's like that, and it doesn't cross. If you want to punch it into your calculator, you can. But I'm hoping by now you know that anything squared or quadratic looks like this, and it's not going to be 1-to-1. The other thing we might ask you to do with inverse functions is to show how to prove, if you will. Now, one way to show it is to plug numbers in and say, oh, if I do 1, 7, I get 7, 1. The other way is to prove them by plugging them into each other. So we're going to take G and put it into F, and then we'll put F and put it into G, and let's see what happens with the answer. So if I write F down, right, and I put the G in there, I'm also going to write G down with an open X, and then I'll put F in there. Okay, so I'm saying F, this is F of G of X, and this is G of F of X. All right, now what happens? The 3's cancel out. I get X plus 5 minus 5, which leaves me with just an X. What happens here? 3X minus 5 plus 5 is 3X over 3, which equals X. This is how you can prove that two equations are inverses of each other, because when you plug them into each other, you're left with just the letter X. So if you see the words prove, more than likely this is what they're asking you to do. They're asking you to show both of those. Okay, does that make sense? Is that coming back from the rest of what we look at is easy. Why are we talking about inverses? We're talking about inverses because logs and exponentials are actually inverses of each other. So let's look now. Can you read from a table? Don't look at these yet. I want you to try to do it from just this, and if it's confusing, then we'll break it out into different tables, okay? So I'm going to highlight mine so I have different colors so I could talk about the different things. This is reading from a table, okay? So these are your X's, your X values, and this is a table. So these are your XY points, -2, 5, -1, 2. And then for the G equation, your points are -2, -3, -1, 4, okay? Now remember, when we look at the inverse, we read backwards. So let's try this, and then if it's bothering you that way, I'll show you how you can make two new tables so that your inverse is always clear. So this says find the inverse of G at 2. That means you're going to look, normally this is our X value, but because it's an inverse, that's our Y value. So you go to G and find a 2, and you read back up to see that X is 0. Is that okay? Okay, we're going to go on. This says, here's your outside, here's your inside. We always do the inside first, then we take our answer and put it into the outside. So we're going to find this one. Now remember, there's an inverse, so that tells you to look at Y. This is F, so you go to F and you look where Y is 1. Y is 1 here, that means X is 2. So now they want us to find G of 2. Now this is just the G function, it's not an inverse, so that's your X value. So go look where there's a 2, and now look down to see what G is. G is 7. Okay, this is just F of 2 minus G inverse of 2. So F of 2, that means this is an X. Inverse means this is a Y because X and Y are switched. So F of 2, go to F, that's 1. Now inverse G of 2 means you look at G's Y value of 2. And if G is 2, X is 0. Is that okay? All right, try this one on your own. I'll give you a second, and then we'll do it together. This is inside, outside. That's important thinking pattern for calculus. So Now, because this says inverse is the 7 and x or a y. Because it's an inverse, the 7 is y. So go find a g where it equals 7. Right there. So go back up and the x is 2. Now we're going to take that 2 and plug it into the outside. Now, this is an inverse, so do we look at x or y? We look at y. So we go over to where y is 2 and x is -1. This is f. F is 2 right here, and x is -1. Does that make sense? Okay, if you need a minute to write some notes down, go ahead. All right, we went through all of that, looking for inverses. Why are we putting inverses here? Because now we have to look at logs and exponentials. Exponentials are really easy for y'all. You know things grow exponentially. If I spread a rumor around, it doesn't even take till noon to spread around the school, right? Or germs. Y'all are familiar. We're washing our hands all the time. You know that germs spread exponentially. But when I ask you about a log, you're like, yeah, I don't get a log. So hopefully when we compare the two, you'll be like, okay, I get a log. So let's do an exponential first because you know that. You're good with exponentials. So let's take these numbers and plug them in here and find out what y would be. 2 to the -2 is what? Well, 2 squared would be 4, so negative to the -2 would be 1 over 4. If you plug -1, 2 to the -1, right? Means 1 over 2. Plug 0, 2 to the 0 is 1. Any number to the 0 is 1, except for 0. 2 to the first is 2. 2 squared is 4. 2 to the third is 8. So to find the inverse of this, you simply switch x and y. So these are going to become your y's. These will be your x's. See how easy that is? Woohoo! Now I want you to notice something. We're going to practice this more when we look at properties and equations, but I want you to look at something. Notice this is 2 to the x, and this is log base 2. It's not a coincidence that this matches this. Okay, we'll get into that more when we learn how to rewrite logs and exponentials and go back and forth. But I want you to notice I specifically picked 2 so that they would be inverses. If this was a different number, they wouldn't quite be inverses of each other, okay? So let's graph these. I'm going to graph, well, I'll graph this one in purple. So we're at -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. Here we go. And you guys know that logs have an asymptote and exponentials have an asymptote. So for the exponential, it's right underneath this special point. So there's your exponential graph. This point and this point are very special. I like to refer to those as pivot points. Because notice something, even if I made this 3 to the x, 5 to the x, even if I change this equation, anything to the 0 power is still 1. So 1 is always there, okay? Now let's graph our log in green. So we're 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2. Okay, and an exponential has the asymptote underneath, and you notice the log has an asymptote, right? This is x equals 0. This, of course, is y equals 0. And then notice from one of our rules that you may have forgotten back here, we said it's a reflection over the line y equals x. So if you put this line in, it's a mirror image, right? It's reflected across that line. So think about some things now. When you look at an exponential graph, it grows very quickly. We're kind of even, and then we skyrocket. Notice a log graph grows very, very slowly. It's barely going up. It will continue to go up forever, but it's going to go very, very slowly. Okay? Now, the cool thing I want to show you, you've got to remember these 2 points. An exponential is 0, 1. A log is 1, 0. Now, how are you going to keep from getting those mixed up? You cannot mix those up. Look at this. How do you spell log? L-O-G. And what does L-O look like? 1, 0. So you'll always remember that the log is the one that's 1, 0. Exponential is 0, 1. Okay? Now we can move them around, but that's always going to be our starting point. You know how with a parabola, you have the vertex and you move it around and draw your new curve? These are your pivot points because we don't have a vertex, so to speak. Okay? So let's look at a couple review questions and we'll be done. Not too bad, right? Okay. So let's look at some exponentials first. We know what an exponential looks like. It's supposed to go through 0, 1, right? So what we'll do is we'll take that point. It should go through here. That's the starting point. But what does this one do? Anything with the x affects as the x direction. It's backwards. So this goes right 3. And I don't want you to have to worry about making tables of values. I want you to know that the logs and the exponentials always have the same basic shape. So we're just going to take what would be our start point and go right 1, 2, 3. And then we'll just draw our graph. Now, you could draw a graph like this, right? Or you could say, well, I think it looks more like this, or I think it looks more like this. And it is true, as we change the number 2, your graph can become sharper, steeper, or it can become less steep. But right now, I'm interested that you can just get the basic shape in. Okay, so I'm not worried that you make a table of values. I want you to know with your eyes what it looks like, because really we're in pre-cal, preparing you for calculus. And guess what? In calculus, we want to know which way the end is pointing. So I need you to know that this end goes up, and I need you to know that this end gets closer and closer to the asymptote. That's it. All right, what does this one do? Down 4. So I should start here. I'm putting a little x. X marks the spot. Now go down 4. 1, 2, 3, 4. There you go. I'll put my asymptote in underneath that dot point. And now you just get that, right? So there's your pivot point. Here's your asymptote. Not bad, right? Okay, a negative out here. That's a reflection in the x-axis. What's the outcome of that? We're upside down. Or if you want to think about it, x-axis is the mirror, right? I'm going to draw in the parent for this one because I want you to be able to see a mirror image. Sliding back and forth is easy. We just count, but I'm going to do this one in gray so it's nice and light. So it would look something like that, right? This negative means that That's your mirror. So you're going to take this and flip it down. So what's the mirror image of this? Right there. Or if you remember, when we have the negative out here, it changes the sign of y. So 0, 1 becomes 0, -1, right? Y changes sign whenever you have a negative in the front. Or you could think about a mirror image, whichever makes you happy. There's a new pivot point, right? And remember, we've been studying transformations, and they stay the same whether you're looking at trig functions, parabolas, polynomials, logarithms, and exponentials. The rules stay the same with our notation, correct? Okay, so this is a reflection in x. We already know that. And this negative is a reflection in y. So I'm going to draw the parent again, just so we have a visual. All right. So if I were to flip that over and turn it upside down, it would look like that. That takes care of this part. Now I'm going to do this part. That switches it this way, right? Then this y-axis is mirror, right? So think about your y-axis as the mirror. So what's this going to look like? Right? Go. So I'm going to be over here. And I'm going to come down. I still have my asymptote. Right? So we took this one and we flipped it. Right? If you have trouble graphing these, are you allowed to say, okay, I need some new points on this? Are you allowed to plug numbers in and get a set of points out and graph points if you need to? Absolutely. But I'm hoping that you are remembering, if you know what the parent looks like, you can use your transformations to get the general idea. So what's the end game with this? I want to know that this end is going to travel forever and get close to 0, closer and closer to 0. And I want to know that this end is going to go down to -infinity. That's where my end game with this is going, okay? So we practice with an exponential. Let's practice with a log. So we know what a log looks like, right? It spells its name, L-O-G, goes through 1, 0. So it should be right there. And it grows slowly. So I should be here. But what does that do? Right? That goes left 3. So we're going to count 1, 2, 3 and put our new point on. The asymptote is next to the dot. And you are simply going to get very close to your asymptote, and then you're going to pivot, okay? That's as close as I need you to get. I want you to see where it is. This one, down 5. So I'm supposed to start right here, but I'm going to go 1, 2, 3, 4, 5. There we are. So we haven't moved right or left, so we still have an asymptote right there. And we're going to come up. And we bend slowly over. I don't know exactly if it's here or there. We could plug numbers in if we wanted to, but we don't have to do that, right? This one again, that's a reflection in the x-axis, so it's upside down. Or you can think of x-axis is mirror, right? So we're supposed to start right here, right? And we should do this. But now this is going to flip it over, right? So it's not going to change where our asymptote is, but Instead of coming down and going up, we're going to come from the top. All right, one last one. This one is a reflection in the y-axis, right? So this means y-axis is mirror. So I'm going to put my, let's draw in, well, I went crooked, didn't I? There we go. This is what it was supposed to look like, right? Through here. But this is going to be a mirror image. So this is your mirror. So if I'm at 1, 0, I'm going to be at negative 1, 0. And remember, we're switching the sign of x because our x is there. So instead of coming up, I'm going to be on this side. Does that make sense? I hope. All right. And a good question came up yesterday. Let's look at this real quick, and then we'll look at what our homework is. Let's go into here, right? Well, and let's do 2 to the x and 3 to the x. I want you to see how things change, and 4 to the x. Let's look at how the graph changes as my number gets bigger. You can see as the number, as your base number gets bigger, your curve gets steeper and steeper. Okay, does that make sense? Now, if we, whoops, so if the exponentials are getting steeper towards the y-axis, what are the logs going to do? Are they going to get steeper and bigger, or are they going to get closer to the x-axis as it gets bigger? Let's look. So I'll clear these. And we'll do alpha window. That'll allow you to have your log base. Alpha window 5, right? And I'm going to do a 2. Then I'm going to do alpha window 5. And I'm going to put a base 3 in there. And alpha window 4. What did I just do? Alpha window. Okay, now remember, the exponentials got closer to the axis as they got bigger. Let's see what happens to these. What do you think is going to happen to the logs as that number gets bigger? They do the opposite of what the exponential did, right? Remember the exponentials, they're symmetrical. So if the exponentials get bigger and grow this way, the logs are going to get bigger and grow towards the axis. Okay, so that is it for notes today.